Good day and welcome back to part 3 of our discussion on maximum and minimum values. In the previous video we discussed critical points and how to find them computationally, but we left ourselves with a question to answer. How do we go about classifying critical points? When we were in Calculus 1 we had things such as the first derivative test and the second derivative test. And in Calculus 3, for functions of multiple variables, the second derivative test, which I will oftentimes abbreviate as SDT, is going to be the test that will allow us to classify critical points. So suppose that the partial with respect to x and the partial with respect to y are both equal to 0 at some input, AB. And note, that is just telling us that AB is a critical point of a function f of two variables. So if you are at a critical point of a function of two variables, the second derivative test is going to allow us to classify that critical point, and in order to do so we need to make an auxiliary computation to find this quantity d. Now because d does depend upon that critical point AB, oftentimes we will use the notation d of AB, and it is defined as follows. It's fxx at AB times fyy at AB minus the square of fxy at AB. And recall from a previous discussion with partial derivatives that those mixed partials are equal. So if you prefer, you could use f sub yx versus f sub xy. And what this quantity is going to tell us is the following. If d is bigger than 0, what that's going to imply is that we have a local max or a local minimum. And if d is less than 0, that's going to guarantee that we have a saddle point. And I'll also, before explaining anything else, note you may be wondering, d bigger than 0, d less than 0, what if d in fact equals 0? And it turns out that if d is equal to 0, the second derivative test is inconclusive. Similar to going back to our Calc 2 experience with things like the root or ratio test, it's very possible for something to be inconclusive, and that just means it tells us nothing. We would have to do a further investigation. And I will also add in here that for us, this would be a very rare scenario that we will most likely not encounter. Now, going back to the second derivative test, if d is less than 0, we're done. We just simply say we have a saddle point, i.e. not a local max or min. Now, if d is positive, that's an indication that we're going to have a local max or a min, which means we need to do some further investigation to determine which one it would be. And this is where our Calculus 1 intuition is extremely helpful. If the second partial f sub xx at AB is positive, and just think back to Calculus 1, when that second derivative is positive, we're really considering this to be concave up, and if you are concave up, you of course have a local minimum. Similarly, if that second derivative is negative, you're visualizing something which is concave downward, and if you're concave downward, you have a local maximum. So our Calculus 1 intuition can really help us kind of remember and work through that second part. One other thing I wanted to note before diving into an example is sometimes there can be difficulty associated with remembering the formula for d, and one way we can remember it is as a 2 by 2 determinant. So I'm going to think x, y, and you'll see why in a moment. And going across the x row, that's going to tell me the first partial derivative I calculate. And going down a column, that will indicate the second partial derivative we calculate. So in this first column, we have fx as our first partial. But in that first column, it's fxx and then fxy. Similarly, in the second row, we start off with the partial with respect to y, and then the second column gives us the next partial. And if you were to write down this 2 by 2 determinant, remember you multiply down the main diagonal, you would have fxx times fyy, and then we subtract away what we get when we multiply down the cross diagonal. So we are subtracting away fxy times fyx. And if we remember our observation from above that those mixed second partials are really equal to each other, that is precisely the quantity that we do have with D. So if you need a way to help you remember the formula, that could be a convenient method. And let's go ahead and put this into practice. So for the example given below, let's go ahead and find and classify the critical points. And we'll very quickly see that examples do get quite a bit messier computationally than in our previous video where we started off with some nice simple examples. So in order to find the critical points, we need to know the partial derivatives with respect to x and y, and then determine where are they simultaneously equal to 0. If you calculate the partial with respect to x, we would have 2x plus 2y, and the partial with respect to y is 4y cubed plus 2x. And we want to know where will these simultaneously be equal to 0. And this presents us with our first difficulty. How do we solve these two equations? And the general rule of thumb that I'll give you, and we'll use over the next few sections, is you work with one equation until you have enough information to substitute into the second. And I typically choose to start off with whatever equation is the simplest. So in this case, the first one. So we will manipulate the first equation until we have something we can plug into the second. So the first equation tells us 2x plus 2y is equal to 0. Dividing by 2 implies x plus y equals 0. And now we can either solve for y in terms of x or x in terms of y. So y equals minus x. What I would like to do is take this information, i.e. maybe an alternative way of writing y, and substitute it into the second equation. So let's go ahead and continue on with our work. 4 times y cubed, we're making y minus x, plus 2x is equal to 0. And note the power of this is that once we've solved for y in terms of x, and we substitute that into the second equation, we now have an equation involving only one variable, which is much more familiar for us to work with. So if we go ahead and just expand things out a bit, we would have minus 4x cubed, because a minus cubed is still negative, plus 2x equals 0. So both terms contain a 2 and an x, and I'll go ahead and pull the minus out as well. That would make what's left over a 2x squared minus 1. And if I'd like to know where that quantity is equal to 0, that means the first term in the product is 0, or it means the second term in the product is 0. And that would imply x squared is 1/2, or x is equal to plus or minus the square root of 1/2. And we now have a complete description of our critical points. So a critical point would correspond to some ordered pair, x comma y, that simultaneously solves both of those first partials equal to 0. And what we've learned is that if we combine everything together, we will have a critical point when x is equal to 0, or x is equal to plus or minus the square root of 1/2, and then the key observation is to remember the first equation. We have to come back to that with y equals minus x. So the critical points are as follows. When x is 0, we know that y is going to be minus 0. And then there's two other possibilities for x, the square root of 1/2 and minus the square root of 1/2. And remember, whatever x is at our critical point, y is going to be the opposite of it. So the first critical point occurs at square root 1/2 minus the square root 1/2. And that second one corresponds to minus square root 1/2 minus a minus, so positive square root of 1/2. So we have 3 critical points. And to quickly recap, we solve these equations simultaneously by working with one of them until we have enough information to plug into the other equation. But once you end up with these x values, we have to remember this equation to get the corresponding y values. Now we get to the heart of the matter. We have these 3 critical points. Are the critical points going to correspond to local maximums, local minimums, or neither? And in order to answer this question, we are going to apply the second derivative test. But the second derivative test requires a few more derivatives. We need those second partials. So fxx, fyy, and I'll go ahead and find fxy. So the second partial derivative f sub xx is 2. F sub yy, looking directly above, we see is 12y squared. And f sub xy is also 2. So d, the quantity we need to use the second derivative test, is equal to f sub xx times f sub yy minus f sub xy squared. So in our case, if we substitute in those values, we have 24y squared minus 4. And in order to classify our 3 critical points, the first step is substituting in those values. So we have immediately d of 0, 0 is going to be 24 times 0 squared minus 4. And note I'm not particularly worried about exactly what number that is. I just want to know its relationship to 0. That's a negative quantity. And the second derivative test tells us that when we have a negative quantity at a critical point, that would imply that the critical point 0, 0 is a saddle point. And we have 2 more critical points to take care of. So d at this next one, square root 1/2 minus the square root of 1/2, would be 24 times minus the square root of 1/2 squared minus 4. And once again, I don't need to worry too much about what this number is, but note a minus when it gets squared is positive, and the square root of 1/2 squared is 1/2. So 12 minus 4, it ends up being 8, which is a positive quantity. Similarly, d of minus the square root of 1/2 positive the square root of 1/2 ends up being exactly the same, which is positive. And because d at these remaining 2 critical points is positive, we know that we will have a local maximum or a local minimum. It all depends upon that second derivative. And it's worth noting we can use either one of these second derivatives that we would like. I would typically just pick the simplest one to work with, 2 in this case. So observe that in either case, the second derivative is equal to 2, which means it's positive. And if your second derivative is positive, remember we're thinking that would indicate something like concave upward, so you would have a minimum. So 0, 0 is a saddle point, and we know the square root of 1/2 comma square root of minus 1/2, along with that final critical point, are both local minimums. And this completely answers the question that we've been asked, that is to classify the critical points. There are 3 critical points. At the first critical point, this d value is 0, which means it's a saddle point. At the second 2, it's positive, indicating a local max or min, but because the second derivative, f sub xx, is always positive, they must be local minimums. And I'd like to finish by making the observation that This was a somewhat lengthy and even kind of computationally involved problem for a relatively reasonable function f that we started with. So we will see many computations of this form in the upcoming 2 sections. So as usual, I'd most definitely recommend spending some time practicing examples. You can find plenty of good suggested problems in the book. Feel free to reach out to me with questions. In the next video, we'll explore one more of these examples involving the classification of critical points, solely to become more familiar and comfortable with these algebraic techniques. So stay tuned and take care.